Okay, theorem. If the sum from n equals 1 to infinity of a sub n converges, then the a sub n has to converge to 0. Okay, there's two different things we're talking about here. Remember, this notation, I need to remind you, this notation, when you see a sub n arrow 0, that means the limit as n goes to infinity of a sub n equals 0, right? That's alternate notation. So a sub n converges to 0. So we're talking about two different things converging here. The sequence given by a sub n, and in the first case, the series itself converging. So what are we saying, what are we not saying? Okay, if this series has a chance to converge, or does converge, I should say, then a sub n has to converge to 0. If you're summing, remember what this notation means. It means A1 plus A2 plus A3 plus A4 plus ... on forever and ever and ever. If those A subscripts whatever don't converge to 0, then you're adding non-diminishing terms. How could the series ever converge if that's the case? So that's my hand-wavy proof, but it's a pretty good one. And that's an intuitive explanation, but it's a pretty good one. Does that seem reasonable? So really, that notation, what does a sub n arrow 0 mean? It doesn't mean it equals 0. It means
it approaches 0.
The limit as n goes to infinity of a n equals 0. That's the other notation, right? So if you only want to use one notation for limits converging, I would actually have you use this one. Even it's obvious why we like the other one, the a sub n arrow 0. That's less to write. Okay, so everybody believes that theorem. That's not the form we use to show convergence, though. This is just a necessary condition for convergence. Just because a sub n converges to 0, it does not mean that the related series converges to 0. That's a big warning, because that's a big misconception. Okay, warning. A sub n converging to 0 does not necessarily mean that the related series n equals 1 to infinity of a n converges. It's simply a necessary condition. In order for that series to converge, a n must converge to 0. So what we get from this is a test for divergence. So because a n converging to 0 is a necessary condition to have the series converge, we can't use it to prove convergence of the series, but we can use it to prove divergence. So the idea then is this. We rephrase that above theorem into something that's equivalent. Call it the nth term test for divergence. And the nth term test for divergence is this. Here's a nice short notation. If a n, okay, how could we say doesn't converge to 0? That means it does converge to 0. How about just put a line through it? If a n doesn't converge to 0, then the series I equals 1, I've been using n, sorry. N equals 1 to infinity, a n diverges. That is logically equivalent to saying if the sum converges, then a sub n converges to 0. So this is your first test. It'll tell you whether or not a series diverges only. It won't tell you if it converges. Okay? So just because a n converges to 0 does not mean the series converges. Big idea there. A classic example, the sum, this is I think called the harmonic series. The sum from n equals 1 to infinity, 1 over n converges to 0. Agreed? That's our a n in this case. Just 1 over n converges to 0, but it turns out that series does not converge. And we'll talk about that more perhaps today, if not today, tomorrow. So this diverges. So this is a counterexample if you're thinking that the fact that 1 over n converges to 0 means the series converges. This diverges even though 1 over n converges to 0. That's a mess, so let me move that. And this has to do with the warning above.
So if we find out that it doesn't diverge, wait, so if our divergence test doesn't work, then it doesn't mean that it converges?
If an does converge to 0, you haven't proved a darn thing.
Okay.
It's only if it doesn't converge to 0 you've proved that the series diverges. Example, you're going to get sick of this question. You're going to see it a lot. Does it converge? We have the sum, and we don't even care what it converges to a lot of times. Just does it converge? Does it converge? The sum n equals 1 to infinity of n divided by 2n plus 3. What do you think?
We know that it doesn't, I mean, we need to test it for convergence.
Okay, but what's the only test we really have if it's not telescoping?
We have to test for divergence.
Okay.
And it does not.
Okay, so you're going to look at an. What's an in this case? N over 2n plus 3. And I don't think, you could use some of the machinery we developed, but if it's a rational function, polynomial on top, polynomial on the bottom, I'll let you use the degree test. If the degrees are the same, numerator and denominator, take the ratio of the coefficients to get the limit. What's the degree of the numerator? Oh, that looks like ln. Let me erase that 1. What's the degree of the numerator? 1. Degree of the denominator? Nope. It's the highest power, right? It's 1. So what does this guy converge to? 1 over 2, the ratio of the lead coefficient. If you didn't believe that, you could look at the related function f of x equals x over 2x plus 3. You get the indeterminate form infinity over infinity, and you can use L'Hopital's rule. That'd be one way to do it. Or just divide top and bottom by n. Or multiply numerator and denominator by 1 over n, same thing. Okay, does this equal 0? Does 1/2 equal 0? Nope. So what's your conclusion? So the series, here's what you do need to write a conclusion statement. The series diverges by. Okay, can we shorten the nth term test for divergence to just the nth term test?
Yeah.
Shorten it to just the nth term test. Diverges by the nth term test. I suppose that should be capitalized. Good thing it's not an English class. Okay?